Okay. All right. So I'm not sure how far you guys want to go with this material. It just kind of depends on how confident you're feeling and how much load you can take into your brain. So you have done your Lewis structures. Now the next step to it would be shapes, and then we'll see how you guys feel if you want me to cover polarity as well. As I was saying, with this question, Lewis structure, shapes, and polarity, you need to get that Lewis structure right. If you get that Lewis structure wrong, it's going to snowball, and then when you start describing the shape and you start using that shape to explain polarity, it's not going to work, and you're going to miss out on the whole question because you don't have your shape correct. Okay? So first thing to always do is double and triple check that Lewis structure because it has really dire consequences if you get it wrong. So we're going to actually use the Lewis structures from last week's tutorial because they're already drawn out and we know that they're working. So we know step number 1 with any shape is figure out the Lewis structure, right? So I'll write that down as our first step. Figure out Lewis structure. And that's going to be really important because that then helps us understand how many regions of electron density there are, how many bonds there are, how many of those are in bonds, etc., etc. So that's the first thing to kind of keep in mind with our shapes question, is doing that step. Next, when it comes to writing these answers and when you're trying to justify shape, I'll talk about what you guys did last year and then I'll bridge into what's going to happen this year. It's very, very similar, but there's a little bit more focus on other components to it since it is a slightly larger molecule. So first off, you figure out the Lewis structure shape. Then once you figure out the shape, that's okay, is you're going to count the regions of electron density. So figure out Lewis structure shape, second step, count regions of electron density around the central atom. Does that ring a bell to you guys? So we're talking both about bonded and unbonded electrons. I should actually probably do this in different colors so that way I can actually note it when we're looking at our Lewis structures. I'll change the color for the next one. All right. So if we're starting to do that process, in this first example, you see how I have carbon dioxide? Remember that double bonds are still counted as one region. They're not two separate regions. So if I was trying to figure out the regions of electron density in this one, there'd be 2 regions. Okay with that so far? If I was looking at this one down here, that has 1, 2, 3 regions. Again, remember, if you have anything with a double or a triple bond, it still counts as one region, even though it is a multiple bond. Next one we have, looking at our examples from last week, this one has 1, 2, 3, 4, 5 regions. This one here has 1, 2, 3, 4, 5, 6 regions. Remember, those lone pairs of electrons are counted as a region. Did I do one more last week? I think I did. I did one. Oh, I did 2 more. All right. This one here, 1, 2, 3, 4 regions. And then this last molecule that we did the other day, 1, 2, 3, 4, 5, 6 regions. So that's your first step. We good so far? All right. That is really important when we're starting to figure out shapes and what they are potentially going to be, because those number of regions, when we apply VSEPR, you guys remember VSEPR? We can use that to determine bond angle. So this is used to justify bond angle. And the main way you're going to justify that is using the VSEPR. So that VSEPR theory was that theory talking about how because they're all negatively charged, they're going to try to separate to maximize distance apart and minimize repulsion. And that's because you have electrons are all negative charge. The like charges repel. Does that ring a bell to people? All right, let me go and show you guys the PhET program just to kind of help us visualize what's going on. So for example here, we'll show the bond angles as well. That kind of helps us out. And do I want the electron? No, we won't worry about shapes at this point. So you see here how this is a 180 degree. I have two regions of electron density. If I add another bond, I now have another region of electron density, and now I have 120 as the angle. And you guys were used to justifying this last year. If I get rid of that and put a double bond there, that double bond acts as 1, not 2. If I add a lone pair of electrons, same thing happens. It makes it that double bond. So all of those factors, regardless of if we're talking about bonded or unbonded, it's going to influence the shape of what we're going to get molecular-wise. If I add another lone pair of electrons, again, it changes it as well because it's trying to maximize the space from each other.
So now it's got 4 regions.
So now it's got 4 regions. Okay. And if we want, we can start looking at things now with 5 regions. Now, this should actually help make my next point. This year, they're not going to be asking about bond angles. The reason why is because when you start looking at some of the geometry of these shapes, it can get quite complicated. I'm just going to put a few more bonds in there because when you turn it around, you'll notice that some will have 120 as an angle and others will have 90 degrees as an angle. And so it just becomes this job of memorizing bond angles and where they locate geometrically, and that's not a useful thing to be assessing on. So this year they don't focus on, do you understand the bond angles? But I'm just pointing it out as a nice little refresher from last year. Are we okay so far? All right, we'll go back to the notes. So that is our first step, is to count the regions of electron density. That helps you basically figure out overarching categories. And then next step, what you're going to do is you're going to check how many of those regions of electron densities are in bonds. So step number 3, compare bonded and unbonded electrons basically. And that is really important because that information then you use it to justify shape. The thing to remember about these unbonded electrons, or these lone pairs of electrons, you might refer to them as, is that they affect shape but are not drawn in the final shape. And the thing about this year is that now we have some more shapes to deal with because you're adding up to 6 regions. Are we okay so far? Keep going? Oh, I still see some pens going. The other thing I would like to add is when you're thinking about structure, this is basically how you would structure the answer when you're writing your justification. Make sure when you finish your answer, you are going, therefore, this is the shape. Clean it up nicely. Make sure you're using words like because. All right, be really, really clear on what's going on. Like, use the symbols of the atoms you're referring to. Like, this is the center atom, and these are the surrounding atoms, that sort of stuff. So this would be a spot where you'd use therefore and then say what shape it is and why. Or you've already said why. You just kind of do another kind of final. Those 3 dots mean like therefore. So just be mindful that that's a place where you can kind of close part of your answer. Right? So when we're looking at that, be mindful you use this sheet here to help you out. So like I said, first is to figure out the number of regions. So this is a nice diagram because it shows you, okay, 2 regions, 3 regions, 4 regions, 5 regions, 6 regions. I figured out the total number of the regions. Then you ask yourself how many are bonded or not in bonds. And it says on the top, non-bonding pair, non-bonding pair, or sorry, no non-bonding pair. 1, this one's 1, this one's 2, that one's 1, 2, 3. So it gives you an indication of number and how that then influences what the shape is going to be. So there's that sheet here. I like how this one outlines it, but I also like this one here too because it kind of shows it as a table. And you can think about like the intersection of how many regions of electron density there are versus how much or how many of those are in lone pairs. And that will then tell you the shape. So obviously you guys have done up to this part here. And now you're adding these 2 lines of shapes. So it's just some new things to memorize. Again, some of the shapes make sense, some of them don't. I'll show you on the diagram because some of them do kind of look like what they're supposed to look like. But that's how you do your shape stuff. So let's go back to the PhET software. I'm just going to clear everything so we can start over and we can start seeing some of these other molecules. So if I have 5 regions of electron density and they're all bonded, 1, 2, 3, 4, 5. This one is known as a triagonal bipyramid, and I actually think you can see this one. So if I'm just trying to move the little guys around. So you see how this here is a triangle, and then that goes upward, and it forms a pyramid. So bipyramidal 2 pyramids. Just like when you guys had the triagonal pyramid. Let me just get rid of that, and we did that. So that was the triagonal pyramid shape, and you see how it looks like a pyramid structure there. So a lot of the things look like what you think they would look like. The next one, if I take away one of the bonds and I replace it with a lone pair, this one is our sawhorse, is what it's called on this sheet. On the other sheet, it's called a seesaw. That one's a very silly name, but the name kind of makes sense when you look at it. So if I flip this guy around, I'm just trying to move it so you can see it. It's kind of like a seesaw because you have these 2 things on the ground and then these things go up and down. So it does look like a seesaw. Yeah, these silly names. This one here is your T shape. So it looks like a T. There you go. Looks like a T. That one's a T shape. Okay, get rid of another one of those bonds, put this guy in. This one's linear, because you see how it's a straight line, like the linear shape you guys are used to seeing anyway. Cool. Let's go to the octahedrals. Oops. Okay, so that one here is your octahedral shape. I don't know how a good way to remember that one. Or place that with a lone pair, and then that is your square pyramid. Let me move it around so you guys can see it. So you see how that base now is a square, and then there's one little point up there. That is my pyramid, so square pyramid. Yeah, Charlie. I don't know.
Oct is 8.
Yeah, oct is 8. That's why I'm like, I don't know why they've called it octahedral. You guys can Google it and find out. All right, so that's that one. Let me add another. This one here is known as your square planar. Very similar to what you guys had last year with the triagonal planar. It's a square, but it's flat instead of having anything that's pointing out, making a pyramid. And then get rid of that guy, add another lone pair. You see how we're once again back to that T shape. Looks like a T. And then get rid of one of those, add a lone pair. Now we're back to linear. All right. So that's how that works. I'm just going to switch back to the document camera. So you'll see with our things that we were doing the other day, you can tell what shapes that are based on the number of regions that are bounded and unbounded. So this one's no lone pairs. So this one would be my octahedral shape. I should have changed colors. Let me get that in blue. I think is what I was writing in. Yep, blue. No lone pairs, so that one's an octahedral. This one here, 4 regions of electron density, so that one's still, and they're all bonded. No lone pairs, so that one there is your tetrahedral. This one over here, 5 regions, no lone pairs. You could also say all bonded. You should do both, I would say, when you're writing. Say how many are bonded, how many are unbonded. In this case, 5 regions, all bonded. That is a triagonal bipyramid. This one over here, 6 regions. We have 2 lone pairs and 4 bonded. So when I look at that 6 and then I'm going 2 lone pairs, that's a square planar. So it's the same process that you guys were doing last year, just with a few more shapes. All right. Yeah, move it. All right, this one here you guys did last year, 2 regions, both bonded. So that is linear. This one here, 3 regions, all bonded. So that one is your triagonal planar. That's all you gotta do. What questions do you have, Charlie?
So you know how like the lone pairs?
Yeah.
They are only regions if they're on the center.
Yes, that's a good question. Yeah, so lone pairs of electrons, we are only concerned about them if they're on the central atom determining the shape. So you're not worried about these lone pairs. Okay? The other thing that you need to keep in mind sometimes that I don't see it so much with level 3, but I see it a lot for level 2, is that they'll give you big, more complex molecules and they'll ask you about multiple locations in the molecule. I'll draw one out just to kind of show you what I mean. It's unlikely you're going to get that because it's not something that they tend to ask at level 3 anymore. So let's say, for example, I'm just drawing out a carboxylic acid. So I've seen on exams, more so with level 2 than with level 3, is that they'll give you a larger molecule and they'll ask you, okay, what's the bond angle and shape at location A versus location B? And so location A here has 1, 2, 3 regions of electron density, whereas location B has 1, 2, 3, 4 regions of electron density. So this is going to be 109.5, and it's going to be tetrahedral.
Oh, so would you like...
and this here would be, 120, and it's triagonal planar.
So you would just consider each of the carbons to be a completely different plane?
Yeah. Or if they ask you a question like that and they have that extended molecule, you then consider each region that they give you as its own separate region.
Okay.
Yeah. And what that just means is that when that molecule exists in real life is that it does have these multiple shapes because there's different bonds going on.
Hmm.
Yeah, Charlie.
If there's 4 regions, why is it 1 9?
So, trying to find it. Here we go. So if I remove all these guys, and I have 4 regions of electron density, it's 109.5. It's how it works out the space between this atom and that atom. Yeah. So what that means is if you had that molecule and you had another molecule, another thing coming off of it, this section would be 109.5. And then if I had 3 atoms coming off of this one, then that would be 120. So the atoms over there would be 120. The atoms over here would be 109. Does that make sense?
Yeah.
So sometimes they give these weird big molecules. They don't tend to do it as much in level 3 as they do in level 2. Level 2, they did it quite often. And it throws students because they're just like, what? It's a huge molecule. So basically, you count the lone pairs of electrons for the area that you're trying to decide the shape. You don't count stuff that's on atoms attached to the central atom. Okay? So like, I'd be concerned about these pairs of electrons because it's attached to the central atom. I wouldn't be concerned about these ones. Cool. All right. I know we're going to do our STEM talk. We'll see who shows up. Did you guys want me to continue on to polarity? Do you want me just to stop here and this is enough information to digest?
I don't mind.
The thing is, like, most of it is like from last year.
Yeah.
So keep going.
I still don't remember this from last year. But
Yeah.
Because polarity is in the question you gave us.
Yes, polarity is also in the question that I gave you, and also the way they structure the level 3 question is
Marking?
Is it like the shape and polarity?
yeah, it's yeah. The way I want to describe it is when it comes to level 3 chemistry, they don't really ask about the bond angle anymore, and they combine, because last year shape and polarity were 2 separate questions. This year, shape and polarity will be in the same question, like the one I gave you guys today, or this week.
Yeah, that's fine.
So do you want me to go through it? Okay. You guys want me to go through it? They voted to go through it.
This is for polarity?
Polarity.
Sure.
Okay. Okay, so let me add in what I just said to the notes. So this is what they would have asked at level 2. And then the other component that they would ask at level 2 is they would have a whole separate section on polarity.
Which is, sorry.
So it used to be 2 different questions, is what I'm trying to say. I'm just grabbing another pen.
Sorry, polarity.
Polarity. So it used to be you had one question on shape and a second question on polarity. This year for level 3, those become one big question. So at level 3, this is one question. It's one, oh, can't really see the whole page. So this whole thing is now one question. At level 3, they don't tend to ask about bond angles anymore. All right. So something just to keep in mind so you guys are aware of that. Cool. So with the polarity justification, what you need to keep in mind, and let me just pull up my notes so that way I remember I hit all the things I was going to talk about. I wasn't expecting to do this section today, but that's okay. I can still do it off the top of my head because I've taught this so many times. Just to find polarity. All right, so, all right, so when you're doing that question on the assessment, the first thing you obviously do is talk about the shape, because you're going to use the shape as part of the justification. The second step then is to talk about if the molecule is polar or not polar. Now there's different layers to doing that. The first thing you need to be looking for is identifying if polar bonds are present. Now I'm underlining the word polar bonds because polar bonds and polar shapes are 2 different things, and I don't want you guys to smash them together. I know they're both using the terms polar, and they both are polar substances, but you need to be careful with, like, make sure you're saying polar bond because that helps specify what's going on. So when we're looking at polar bonds, what you're specifically looking at is the 2 atoms involved in the bond. And basically what you're looking at is, and you're asking the question, are those shared electrons being shared equally? And that is determined based on electron negativity. Is this, oh, we've talked about electron negativity because it's one of the periodic table trends.
Yeah.
Yeah, so this is dependent on electron negativity.
Still circling back on itself.
Yeah, it does. That's why a lot of people like this standard. It's easy to rope learn because it all relates really well together. Yeah. Unfortunately, again, on the assessment, they don't give you a table of electron negativities for you to be able to like compare and contrast specific numbers. So you're going to have to just look at the periodic table and kind of make a judgment off of that. Remember, the right-hand corner is the most electron negative, so that's the fluorine, and then we exclude the noble gases. So what you're looking for is basically those two molecules involved in the bond. Be specific in talking about what two atoms are in that bond. So for example, if I was looking at this molecule here, I would be specifically talking about the phosphorus and chlorine bond. So be specific and just write down what the bond is. Identify which one is more electron negative. So in this case, it's going to be the chlorine. You know, explain what electron negativity is, explain how that's going to impact what's happening and if a polar bond is present. So in this case, when I'm looking at it, chlorine is more electronegative than phosphorus. And what that means is it's going to pull its electrons slightly closer to the chlorine atom. And it's going to make the chlorine atom negative, well, slightly negative. It means then that the phosphorus, because of that absence of the electron not being nearby it, becomes slightly positive. So you should be using these annotations and those sort of drawings when you're trying to communicate across your justifications.
So polarity is just discussing the negativity and positivity of different atoms.
Yep. Yep. So you're talking about the polarity of the bond. And then we look at the overall polarity of the molecule.
Okay.
All right? Keep going. So that's your first step there. Your second step then is to check the symmetry of the molecule. So basically you're asking here, is a dipole being formed? I should actually add that. So use the word dipole. So dipole just means that you have a positive end and a negative end, two poles. All right. Then your second step is to look for the symmetry of the molecule and decide, are the dipoles being canceled? So again, if we go back to the example that we were looking at, or should I stop and let you guys write that down? Just trying to see if there's an example. All right, keep going. Okay. So in this case here, when I'm looking at this molecule, I've determined that all of those are going to be polar bonds. However, when I look at this molecule, there's symmetry. There's negative here, negative here, negative here, negative here, negative here, negative here. And not only is there that slight negative on all sides, but all those slight negativities are going to be roughly the same value because these are all the same bonds. So what's going to happen is that these are going to cancel out, and since they cancel out, my molecule overall will be nonpolar. So I can have polar bonds and still have a nonpolar molecule. Does that make sense? So if you have polar bonds, you can have a nonpolar molecule. If you have nonpolar bonds, then you're going to definitely have a nonpolar molecule because there's no unequal distribution of charge, unless you have a lone pair of electrons somewhere. Trying to think what else I was going to say. And and then you can have polar bonds resulting in a polar molecule. It all depends on symmetry. So for example, this is a molecule that when I do the polarity check, this guy's slightly negative, this guy's slightly negative, this guy's slightly negative, this guy's slightly negative, and this guy's slightly positive. Yeah? So it does follow that pattern of, oh, I have negative and on all sides. But the problem is that this oxygen and this chlorine are two different atoms, and this here is also a double bond potentially, and so these are actually not the same amount of negativity. So this could be more negatively charged and this a slightly less negative charge. And so this molecule here, I would bet, would be polar because there isn't that symmetry. That one down here, non-polar. And I have another website I can show you guys that tinkers with that polarity. Yeah. Huh? Yes, it is. Yeah. I always try to record it. And then I scan all my notes. Yeah. You guys are so worried. I do it. The only time that it doesn't happen is when I forget to hit the sound recording. I hit sound. I double checked it. But you guys should also check me before I start recording. All right. Does that make sense to everybody so far? Yeah. All right. Can I move it?
Yep.
Okay. So the thing that you have to remember about some of these shapes is some of these shapes automatically allow for symmetry and others will, sorry, let me backtrack. There's some of these shapes here that it will not be possible to ever have symmetry. And that's because of those lone pairs of electrons. So you would expect those molecules to always be polar because those lone pairs of electrons have a different sort of negativity than bonded slight negativity because covalently bonded electrons aren't being shared properly. So keep that in mind. So some of the ones that will never have symmetry would be this guy here. So no symmetry. It'll probably be polar. Should go no symmetry in that one. This one again has no symmetry. This one has no symmetry. Even though there's two lone pairs of electrons there, it's not going to evenly balance. It's going to be one like very negative side of the molecule, and then I don't know what the other side. Oh, come on in, take a seat. We're just finishing up our tutorial. This one here doesn't have symmetry. This one here doesn't have symmetry. This one here you might be okay because it's all centralized. This one here doesn't have symmetry. This one here, you might be okay because the electrons are on opposite sides. This one here has no symmetry. That's not evenly distributed. This one here, you might be okay. So I'm just pointing out some of those molecules that tend not to be symmetrical. All right, and so then you guys can answer the polarity now, section 2. Okay. And I'll put a list of the SciPad pages up. So for the question that I gave you guys for your fortnightly question, I know I crossed out polarity. Ignore that. You can actually answer the polarity bit now too. I'm guessing you guys probably will need some time to process it because there's lots of SciPad pages. So I'm happy to flag a tutorial next week so we don't have tutorial. So you guys have more time just to process this material. Does that sound good?
Yeah.
Okay. Cool. I'm probably about halfway through thermochemistry now, I would say.
When there's multiple different like how it was like CL and
Yeah.
will those
Do you want me to?
kind of be
So I'll go through the ones that we did as examples. So these we talked about. That's the notes. This one here, I would bank as nonpolar. This one here, I would probably bank as nonpolar
It's nonpolar.
because it has that square shape potentially, and those two lone electrons. I'm looking for the symmetry.
So wait, does the one with 5.21 is that non-polar? Is that
This one?
Yeah.
This one would be nonpolar because it's all got the same thing attached to it.
Oh, okay.
Yeah. This one here would be nonpolar. This one here would be polar.
So it'd be like, is it like when you cut one section off, it's the same as the other?
Sort of. Like you're just trying to look to see if like the negative charges would cancel out.
So it's not necessarily symmetry and it's actually different.
No, it's not. It's symmetry in a sense of the dipoles and will the dipoles cancel. So that's why you should be writing dipoles. Yeah. So look at the symmetry. Does the dipoles cancel? And then your final step when you're writing your answer there is going, therefore, this is a polar, nonpolar molecule. You should be saying the word molecule at that point. Yeah, I'm really sorry that, like, this is just the way chemistry is sometimes. And then you would go, therefore, it's either polar or nonpolar as your final molecule. I would be careful and make sure you say the word molecule and make sure you say the word bond, so that way you're specific in which one you're talking about. A lot of people get marked down because they don't follow the sequence of explaining it, and they kind of jumble it up. So this is the sequence you want to answer your question.
Yeah.
Because all of it feeds into the next one. Okay? That's it. All right, if you want to stick around for STEM, you can. I'm just going to talk about my life.
We can't get library?
You can go to the library if you don't want to hear the STEM talk. I'm just going to be talking about high school, uni, what else did I want to say? High school, uni, research. I research both in industry and in and academia, and then teaching. So if you're not interested in that stuff, then don't worry about it.